Thank you everyone for joining today. And first of all, good morning and good afternoon to everyone. Um, so we I am Debashri Rai, and we are today hosting this symposium, Rising Star Symposium series from the Special Interest Group in AI and Machine Learning from the Technical Committee on Cognitive Networks. It's an IEEE group, and we are a special interest group in that broader domain. So our chair is Professor Suba. She is from Stevens Institute of Technology, and we are there. We are like four vice chairs. Dola Saha from University at Albany. Myself, Devashi Rai from UT Arlington. Hanif Rawari from RIT. Hanif is here today, and Moinul from George Mason. He's also here today. So with that, we go to the next slide. So just to give a brief introduction about our group, we are growing. We are like right now we are a big group, and we are also growing. So we have almost 500 members in LinkedIn. Please feel free to join our LinkedIn group. Also, you can reach us out directly through our emails. These are our emails. And we also have a website where we generally keep our activities updated. So this is over the past few years. These like last since 2021, we were having some activities which was covering different virtual seminar series within the interest of our special interest group. So we had hosted various seminar series from various distinguished professor throughout all over the world. And these are the link, and you can have all like their recordings from our websites. This is our website. And we also have mostly these recordings available in YouTube channel. So with that, this is a very new initiative, and this initiative we started actually in last 6 months. We started in fall 2023, and this is so the motivation of this new initiative is to open up our community to emerging scholars and new the rising stars of this domain. Like senior PhD candidates and postdocs to present their work in the broader audience. So our talk, like these talks or these events are intended to foster more mentorship and employment opportunities. And we encourage the speakers to keep these talks within 45 minutes in a job talk format, and so that we can have interactive communication after that. So far, without this new initiative, we had 5 talks. Today is our 6th talk. Started with Dr. Chiai Ye from MIT, and then we had Nadia from NIST. We had Muhammad from RIT, and Chengang from University of Oxford. And the last previous speaker was Andre from Virginia Tech. So before we talk about our today's speaker, the logistics are that we request everyone to be muted on entry, and please stay muted throughout the talk, but please feel free to type your questions in the chat box, because we highly encourage that. We want to have an interactive communication, and by the end of the talk, one of us is going to moderate all your questions. So our today's rising star is Nasim Soltani. She is a long-term colleague of mine. She is a PhD candidate at the Electrical and Computer Engineering Department at Northeastern University. Her research interest is broadly applied to AI and ML for wireless communication, and she has published a lot of work in various prestigious venues. So this is just, I couldn't capture all of them. So, but just to mention, like TWC, TVT, like most of the all ComSoc oriented conferences, she has one paper in all of them. So with that, I will just stop talking, and Nasim, please feel free to start. Thank you.
Thank you, Debashri, for the kind introduction. I will start sharing my screen. Thank you, everyone, for being here today. I hope that you all can see my screen now.
Not yet.
Not yet. Okay. Okay. Now, okay. I think you can see my screen now.
Yes.
Okay, perfect.
Yeah, feels good.
Again, hi everyone. Thank you for being here today. I am Nasim Soltani. I'm a PhD candidate at Institute for the Wireless Internet of Things at Electrical and Computer Engineering Department at Northeastern University. My research area is Applied AI ML for Wireless Communications, and the title of my talk today is Deep Learning for Next-G Wireless Communications. My talk has three parts. Part one, that is deep learning for signal classification. Part two, deep learning in the wireless receiver chain. And part three, that is the future work. In the order of the talk today, first I will give you an introduction, then I will bring a use case from part one, that is waveform classification, then another use case from part one, that is RF fingerprinting UAVs. Then I will show you part two, that is deep learning in wireless receivers. We will discuss part three, that is my future work. And finally, we will dive into the conclusion. First, introduction. Wireless systems have evolved significantly from 1G to where we're standing today in 5G from different perspectives, such as achieving lower latency, having higher data rates and bandwidths, and having improved security. A lot of that progress is owed to the improvements in the physical layer. And my research is exactly in this area, using deep learning for improving the physical layer and the physical layer applications. There are different wireless networks, such as Wi-Fi networks, Internet of Things, networks of drones, cellular networks, and other networks that might be for radar signals or federal applications, specialized applications. The physical layer applications in all of these networks are traditionally handled by signal processing algorithms. Increased wireless spectrum usage imposes new requirements to the physical layer applications. For example, security that encompasses both device authentication and secure transmission becomes more important in more crowded networks. Quicker decision-making becomes more important. More noise and interference tolerance is required. And reduced communication overhead becomes more intriguing in more crowded wireless networks. In order to address these requirements, recently researchers have proposed to replace the signal processing algorithms for the physical layer with AI algorithms. My PhD research is in this area of using deep learning applications for the physical layer. I have worked on different topics that can be broadly categorized into two main parts of part one, deep learning for signal classification. In this part, I have worked on different topics such as waveform classification, modulation classification, RF fingerprinting, and RF fingerprinting UAVs. And in part two, that is deep learning in the wireless receivers, I have worked on using deep learning in wireless receivers for improving bit error rate, to improve security, and to improve throughput. And I have this also this other bubble here that is active learning for wireless communication that gives a vision about how to use active learning for reducing labeling cost for labeling training data sets in deep learning applications for the physical layer. And this sort of can apply to both of these groups, so I didn't color this bubble. So first, I am going to bring a use case from part one, that is waveform classification. Wireless signals can be classified from different perspectives of their modulation scheme, their protocol or waveform, their transmitter ID, that is also called RF fingerprinting, and the environmental conditions that they have been collected under. This classification can happen through one of the two alternate paths. We can take the received IQ, form 2D tensors, and feed them to a classifier algorithm to predict a class for us, or we can create a spectrogram out of each received IQ and form 3D tensors to be fed into the classifier algorithm. In the first use case, we are going to do protocol or waveform classification, and we are going to use the spectrogram-based classification. This is a spectrogram, which is a time frequency representation of your wireless channel. As you can see, most of this spectrogram is noise, but you can see some activities here in two distinct patterns. That's because these are two distinct signals of LTE and 5G. So there are two signals in this spectrogram, but can you find any other signal in the spectrogram? Or in other words, can you find Waldo? Now, if you look really carefully, you can see that there is a fade radal pulse that is overlapping with the LTE transmission. Finding or seeing, detecting this radar pulse is a challenging job in this high noise regime. It is like finding Waldo. That is why the paper is called Finding Waldo in the CBRS Band, and it is published in IEEE GlobeCom 2022.
Hi, Nasim.
But what is, yes.
Sorry, a quick thing. Can you remove the Zoom
Oh, yeah, of course.
windows from here? Yeah.
This one I can minimize.
Yeah, maybe, yes. Yeah.
And this one you can also see?
Yes.
Oh, okay. How to remove this one?
So maybe if you can only share the application window, maybe you're
Okay.
sharing the whole screen, that's why.
Yeah, I am sharing the whole screen and that's all I have.
Okay.
So maybe there is a way, let me see. Yeah, I am using Linux, unfortunately. I don't
I
have
think you
many
can
options.
drag it to the left side.
Yes. Oh, yeah, it goes here. Perfect.
Yes. Yeah.
Oh, okay. I didn't know you could see that too. I thought it's just me. Thank
That's
you for
okay.
telling me.
Yeah, sure.
Okay. But now, what is CBRS band? CBRS band is a band between 3.55 and 3.7 gigahertz that is originally allocated to federal applications in the US. This band is recently open to secondary users with a promise that the original residents of this band, that are the radar signals, will be protected from interference. In order to do this, a hierarchical access priority structure has been designed with the incumbent or shipborne radar signals on top of the pyramid, priority access license or PAL users on the second tier, and general authorized access or GAA users on the third tier. All of these users transmit in the band, and their access is granted using a central entity called SAS. SAS grants access to the second and third tier users. However, radar signals can freely appear in the band. SAS receives environmental information from ESC sensors that are deployed along the coastline. ESC sensors continuously monitor the CBRS band, and as soon as they detect a radar signal, they inform SAS, and SAS enforces the second and third tier users to vacate the band. And that is how the radar signal gets protected from interference. So previously, machine learning has been used in the structure of ESC sensors. However, there are two for radar detection, of course. However, there are two missing angles from previous work. One, interference powers higher than what FCC mandated are not considered. And second, unauthorized users that might be transmitting in the band without being registered within SAS, catching them is not considered. In order to address these two shortcomings, we propose an enhanced ESC called ESC Plus that uses deep learning and specifically YOLO version 3 framework to detect radar signals in higher interference powers and detect other signals such as 5G and LTE that might be unauthorized users. We create our data set in the MATLAB simulated environment. We monitor the simulated MATLAB CBRS band for 20 milliseconds with 100 megahertz sampling frequency, and we create a spectrogram out of each observation. In each spectrogram, there might be an LTE signal and a 5G signal that might be in close proximity. And there might be a radar signal that is overlapping or non-overlapping with either one of the cellular transmissions. I want to mention that our data set is fully compliant with the CBRS regulations. However, in the Department of Signal Power, FCC mandates the noise and interference power to be below minus 109 dBm per megahertz. However, in our data set, we go 5 dB beyond this value to create a more noisy and more challenging data set. We create 1,300 plus such spectrograms, and we partition them into training, validation, and test sets with given proportions. We define signal detection as an object detection problem in the spectrogram, and we use YOLO architecture to do this. The way that it works is that if you feed in an image to YOLO, it will detect the objects in that image for you with bounding boxes around them and labels. The problem is small objects that in our case are radar signals might be missed. To solve this, we propose a two-stage detection where in the structure of our ESC+, we take the full frequency content of 100 megahertz, the original spectrograms, and first we feed them to stage 1, that is coarse signal detection. At this stage, wider band signals such as 5G and LTE will be detected. Then we take that detection and crop it and stretch it, which is equivalent in zooming into it, and we feed the stretched detected signal to stage 2, which is fine signal detection. The YOLO architecture at stage 2 is trained on cropped and stretched spectrograms, and it is able to detect the now stretched smaller signals that in our case is radar signal. Here are some steps of how to crop and stretch the detection so that the original boundaries might not be lost. Basically, we define 2 lambda margins and put them on both sides of the detected boundaries and crop the signal from predicted boundaries plus the lambda margins. We calculate lambda margins using our validation set, and it is calculated separately for each signal type in the data set. In the evaluation parts, first, I am showing a spectrogram that is passed through stage 1, and you can see that the 5G signal is detected. However, if you crop this detection and stretch it and pass it through stage 2, you can see that the radar signal that was overlapping with 5G is also detected. For a statistical evaluation, we define 4 metrics of recall, that is the ratio of true positives among all samples. Average IOU, that is a measure of how accurate the predicted bounding box is, and it is calculated as the area of overlap of true and predicted bounding box divided by the area of their union. We count false positives. We calculate average precision, that is the ratio of true positives among all predicted positives. In this table here, I'm showing these 4 metrics for all 3 signal types after stage 1 and after stage 2. We can see that recall has increased after stage 2. Average IOU has increased after stage 2. False positives have decreased for all signal types after stage 2. And average precision has increased for all signal types after stage 2. Regarding radar detection metrics, we can see that we have 100% radar detection rate after SINR of 17 dB. However, FCC mandates or promises 100% radar detection after SINR of 20 dB. So this means that using our enhanced ESC, our proposed ESC, we can relax FCC regulations by 3 dB. And this means that cellular service providers will be able to transmit with higher powers in the coastal regions in the CBRS band. And they will be able to potentially provide better network coverage to the end users. Okay, you saw waveform classification in the CBRS band. That was a part of part 1. And now you see another use case that is RF fingerprinting UAVs. Today's wireless networks are crowded with hundreds and thousands of devices connected to each base station. In such crowded networks, device authentication is an important privacy and security key. And it is important to know each signal comes from which of the devices. Device authentication is traditionally done through MAC ID. However, this method is protocol dependent and prone to spoofing. There are other methods that are physical layer methods for device authentication that are called radio frequency fingerprinting or RF fingerprinting. Some of them are, most of them are, again, similarity based that require a long sequence of data, and they do some statistical analysis to find out which device transmitted a certain signal. But because they require a long sequence of data, and also they do not have very good accuracies, they're not very popular. Other methods are transient state-based methods that are good for low-frequency devices that are sampled with a higher frequency so that you can really see that ramp in the transient state. However, if you have just high-frequency devices that are sampled with comparable sampling frequency, you cannot really see that ramp, so these methods will not work in those situations. On the other hand, deep learning-based methods for device authentication provide higher accuracy with shorter inputs. But how can you distinguish devices just by looking at the physical layer waveform? Or in other words, what is an RF fingerprint? RF fingerprint or device fingerprint refers to the subtle distortions in the transmitter waveform that are caused because of the imperfections that happen in the transmitter hardware during the manufacturing process. RF fingerprint can have different sources. So different components on the transmitter hardware can impose different types of distortions. Here I am showing different distortions imposed by digital to analog converters, local oscillators, power amplifiers, or mixers. You can see some constellations here that the red points are where the ideal constellation is supposed to be. And the blue point is the distorted constellation after that specific distortion is imposed. I should mention that these distortions are very subtle in reality, and here they are just exaggerated for the sake of illustration. And also the fingerprint of each radio is a combination of all of these effects. That is another reason why it is very challenging to understand or to detect the fingerprint of the radio in the physical layer signal. I have been part of a well-known DARPA project called RIFMILS, where we were provided a massive data set of 10,000 devices, 5,000 Wi-Fi devices, and 5,000 ADSP devices. And we were able to provide accuracies as high as 77% for 5,000 ADSP devices, which is unique among the published literature. So RF fingerprinting answers the question that which transmitter sent the signal, and it is run as a black box algorithm at the receiver side that answers and says, for example, transmitter B sent the signal. In RF fingerprinting, we use the other alternate path, which means we take the IQ samples and create 2D tensors and feed them to a classifier algorithm. However, these received IQ samples are long sequences, but we don't feed them all at once to the neural network. We feed them on a per slice basis. So during training, if you have all of your transmissions on your training set with batch size, known batch size N and slice size L, the way that you form your training batch is that you pick N random examples from your training set, and from each example or transmission, you take one random slice with size L. You stack the slices together to form the batch and separate I and Q in the last dimension. So your training batch will have the dimensions N, L, and 2 because of I and Q in the last dimension. And during tests, what we do is we go through the examples on the test set one by one. And from each example, we take all the possible slices and we stack them together and feed them to the neural network as a test batch. So now that we know how to do RF fingerprinting with neural networks on stationary devices, we should also know that they are not the only devices that we are interested to detect and identify. We are also interested in identifying moving transmitters or drones. Nowadays, drones have vast applications in different areas, including space research, military, internet carrier, agriculture, search and rescue, product delivery. Global UAV market size is estimated to reach 27.4 billion by 2026. And in such a large market, in such vast applications for drones, it is important to identify the drone that is the transmitter of each signal. So our RF fingerprinting UAV paper is published in IEEE Transactions on Vehicular Technology in 2020. For this paper, we collected a data set in an RF anechoic chamber from 7 identical, which means the same make and model, identical DJI M100 UAVs that look like this picture here. And we fly these UAVs one by one over a ground-based receiver at the distances of 6, 9, 12, and 15 feet. And we record their signals while they are hovering and transmitting a proprietary waveform that is called light bridge. So if you look at each recording from each UAV at each distance, it looks something like this. We have 4 bursts. Each burst is consecutive and interleaved portions of data and noise. Each burst is 2 seconds, and bursts are separated from each other by 10-second period of pure noise. So if you extract these transmissions and call them examples and create your data set, and if you shuffle them and partition them into training and test, and you train and test the neural network with it, you will get accuracy of 99%, which seems perfect. However, this is not exactly what we want. Ideally, we want to be able to train on the first examples that come first in time, and test on the last one and still get good accuracy. So if we do that and train on burst 1, 2, and 3, and test on burst 4, we will get a dropped accuracy of 49%. We think the reason for this is that hovering-induced variations in the channel vary the signals over time. So what you are training on, burst 1 to 3, is very different from your signals in burst 4, because they have changed over time, because the drones are hovering. And with non-standard waveforms, we do not have the means to equalize the signal and remove the channel effects. Just to show you that this really happens and to experimentally observe the channel effect, we mounted software-defined radios that transmit standard Wi-Fi on UAVs. So in this way, the channel is estimatable, and estimate the channel in 2 different cases of stationary UAV and hovering UAV. You can see that in the case of a stationary UAV, over 600 milliseconds, there is no drastic change in the channel coefficients. However, in the case of hovering UAV, in just 600 milliseconds, the channel coefficients, their magnitude has drastically changed. So this shows that the hovering motion really has this channel effect that varies the signal. So now what should we do? Is there a way to boost the drop accuracy, or are we stuck with this 49% and this confusion matrix? The answer is yes, we have a method that can fix this confusion matrix to some good extent and give us accuracy of 95%. Our proposed method comprises a multi-classifier scheme where multiple identical neural networks are independently trained on different portions of the training set. And at the test time, each test transmission is fed to all of the trained networks, and their predictions are aggregated using a novel 2-level aggregation method. And finally, for each transmission, we have one predicted class after this prediction aggregation. So the way that we train these neural networks for this multi-classifier scheme is that if you recall, we had this sequence of burst 1, burst 2, 3, and burst 4 from each UAV at each distance. We were supposed to train on burst 1, 2, 3, and test on burst 4. So the way that we prepare the training sets for the multi-classifier scheme is that we collect the signals in burst 1 from all the 7 UAVs at all 4 different distances, and we order them in the order of time. And then we partition them into 4 sets. We do the same for burst 2 and burst 3. And in this way, all the examples or transmissions in each of these sets are similar together, have similar channel variations because they are closer together in time. And those channel variations are different from a neighboring set or other sets. So in this way, we are creating, in fact, 12 training sets or 12 sets, and we take 12 identical neural networks and train them independently on each of these sets. So after training is done at the test time, each transmission is fed to all of these neural networks, and each of them have some prediction on different portions of the test transmission. And then those results are aggregated in the first level of aggregation, which is horizontal, and then in a score-based manner in the second level of aggregation, which is vertical and among all the neural networks, to give us one predictive class per test transmission. So the details of this two-level aggregation method is mentioned in the paper, but the gist of it is that what happens here is that the least certain predictions are suppressed through the decision pipeline, and we magnify and propagate the most certain predictions to the end of the decision pipeline. For our evaluations, we use 2 different neural networks, our own version of AlexNet 1D and 1D version of ResNet 50. So apart from the multi-classifier scheme and the 2-level aggregation method, we have another trick that is data augmentation for training robust neural networks, and it is separately published in IEEE Communications magazine in 2020. The way that it works is that after forming the training batch, before giving it to the neural network, we pass it through a data augmentation engine. And then we have an augmented batch that feed to the neural network. The data augmentation engine is nothing but a complex FIR filter whose coefficients are randomly drawn from Gaussian distribution with no mean and standard deviation. The input batch is convolved with the data augmentation filter and gives us the augmentation batch. So as we keep going and creating more batches over different epochs, these filter coefficients are drawn randomly per batch, and the neural network gets exposed to different variations of the training set, and it gets more robustly trained. So we apply data augmentation to each neural network in the multi-classifier scheme. Our evaluations show that our proposed methods for the first level of aggregation and second level of aggregation are beating the existing methods. And also in this table here, we can see that the 49% accuracy that we are getting with single neural networks can be boosted to 91% with multi-neural networks. And also if you apply data augmentation during training to each of the neural networks, we can get 56% with single neural network that is boosted to 95% with multi-neural networks. Here are 4 confusion matrices associated with these 4 accuracy values, and you can see that with multi-classifier scheme combined with data augmentation, we can get this almost good confusion matrix and get a near perfect accuracy of 95%. So now part 1, that was signal classification from different perspectives, is over, and we enter part 2, that is deep learning in wireless receivers. So our first efforts on neural network-based OFDM receivers started with another DARPA project that was called SPIN, Signal Processing with Neural Networks. And the gist of our efforts is published in IEEE Internet of Things magazine in 2022. This is a traditional OFDM receiver chain for Wi-Fi signals, where the recorded signal passes through different blocks of channel estimation, equalizer, demapper, decoder, until we get the final decoded bits. We propose in this paper, to replace the pink blocks, the 3 blocks of channel estimation, demapper, and decoder, with properly designed and properly trained neural networks. Also, during training that happens offline, we deploy 2 different methods of pruning and quantization for compressing the weight metrics in these neural networks and prepare them for FPGA implementation. We also, in this paper, we also show that our neural network-based receiver provides better bit error rate compared to the traditional receiver that is implemented in MATLAB. And the reason is because of the way that we train these neural networks. So now the question is, do neural network-based receivers provide other benefits for us too, besides providing lower bit error rate? To answer that question, first I will show you some simple blocks of what happens to the received signal until it gets to bits. For unsynchronized communication, which is Wi-Fi signals, which encompasses Wi-Fi signals, you have these steps of first coarse synchronization, that is packet detection and coarse CFO estimation, then fine synchronization, that is fine time synchronization and fine CFO estimation, then channel estimation, equalization and phase correction, demapper and decoder, until we get the final bits. And by the way, CFO stands for carrier frequency offset. So we know in the coarse synchronization department, we know that packet detection is important because first you have to detect the packet to be able to estimate the channel and decode it, receive the information inside it. However, I want to show you why estimating CFO and compensating it on the signal is important. What happens if we don't compensate CFO? So to show that to you, I am showing an ideal constellation, 16 QAM constellation here. And the way that we decode and demap and decode the signals is that we plot the constellation, the algorithm actually plots, or let's say, plots the constellation after equalization and tries to associate each of the samples with one of these symbols here. And each symbol is associated with a bit sequence. So this is how the symbol to bit translation happens. So if you don't compensate the signal, the CFO on the signal, it will look something like this. As you can see, no cluster can be observed, and you don't know which cluster or which symbol each of these points belong to. However, if you estimate the CFO and compensate it, you will have clear clusters, and you can simply decode and demap and decode this signal. But how is CFO getting estimated in Wi-Fi packets? So each Wi-Fi packet consists of a preamble, that is the overhead of communication, followed by a data payload, that is the data part. So this preamble is a fixed sequence that comes with every packet, and it is used for different functions such as synchronization and channel estimation. The question is, do neural network-aided receivers need all of the preamble fields? We studied that question in this paper that is called Poronto. It is about preamble overhead reduction with neural networks, and it is published in IEEE Transactions on Wireless Communications in 2023. So here I am showing a Wi-Fi preamble structure that has first a fixed sequence called LSTF, followed by another fixed sequence that is called LLTF. They have different patterns, followed by LSIG, followed by the rest of the packet. In a traditional receiver, LSTF is first used for packet detection and coarse CFO estimation. And LLTF is used for fine time synchronization and fine CFO estimation, and then the rest of the processing happens. We propose to remove LSTF from the beginning of the preamble altogether and use the next field, that is LLTF, to do packet detection and coarse CFO estimation with neural networks. And the rest of the processing, like fine time synchronization and fine CFO estimation, and the rest happen through the traditional blocks. And we call our proposal Toronto. So removing LSTF from the beginning of the preamble is actually very important and beneficial because LSTF occupies up to 40% of the preamble length, depending on the PPDO format that is associated with different Wi-Fi versions. So removing it from the beginning of the preamble can actually significantly reduce the communication overhead and increase communication throughput. So if we want to do packet detection and for CFO estimation with LLTF, we have to, and using neural networks, we have to define those problems for the neural network. We define packet detection as a classification problem where the input is the received IQ with length 160. And this is just because our data set was, the bandwidth was in a way that we had this length for LLTF and LSTF. But our method is parameterized in the paper and it is extendable to all data sets with all different bandwidths and LLTF lengths. And the output is just the packet start index as the predicted class. We define core CFO estimation as a regression problem where the input is the detected LLTF sequence from the previous stage, and the output is just one value, just the estimated CFO. So the way that we define these classes, as we said, is that if LLTF starts from index 0, we label it as class 0. If this starts from index 1, we label it as class 1, and so on and so forth. So the way that we train packet detection neural network is that after forming our training batch, we pass it through this data augmentation engine that we have, another data augmentation. Basically, what happens inside is that LLTF is dynamically shifted in the input window of the neural network, and we also insert random periods of high noise and low noise. So this is just to mimic that when your packet is coming side by side, you might have noise floor, a period of noise floor, or you might have some random data. So this diversifies the training set and again contributes to training a more robust neural network that has all the different classes with all different noise and data variations. For core CFO estimation, the way that we do training is that we first compensate CFO on the inherent CFO on the signal, and then we draw a new random CFO from uniform distribution between minus delta F divided by 2 and delta F divided by 2. And we impose the new CFO to the signal. So delta F here is the OFDM subcarrier spacing where you are supposed to estimate the CFO. And in this way, your neural network gets exposed to different values in the range of CFO and gets more robustly trained. For our evaluations, we use two different data sets. Data set 1, that is Oracle, for training and test, and data set 2 just for test, just to see what happens if the environment changes. So both of these data sets are collected in an indoor environment, but different indoor environments. And both of them are Wi-Fi data sets, obviously. We use two different neural networks, custom neural networks, Toronto large with 1 million parameters and Toronto small with 200K parameters. In the evaluation parts, I try to rush. So in the evaluation part, we can see that packet detection is giving us 100, packet detector neural network is giving us 100% accuracy for both neural networks, Toronto large and small, which means that everything that MATLAB detected, our packet detector neural network is also able to detect. So we use the smaller neural network just to reduce computational overhead. For core CFO estimation, I just skip to the last plot here. This is mean absolute error between the predicted core CFO and the actual core CFO. We can see that if we train the neural network on the Oracle dataset and we test it on the Oracle dataset, the red graph, we have some error of up to 1,000 hertz or 1 kilohertz for SNR of 0 dB. But if we change the environment, but we do not retrain, we just train on Oracle, but test on Arena, we get a comparable error in the CFO. So this shows that our proposed Pronto is robust to environment change as long as we are inside indoor environments. That is what is tested in the paper. But we cannot ignore the fact that we still have some error in core CFO estimation. So we have some error between almost 0 or 1000 hertz or 1 kilohertz. So the main question is, what is the impact of this error in core CFO estimation on the bit error rate? That is because that is what we ultimately care about. To answer that question, we have gone through our test set and we have picked one packet from each distance. And we feed it once to the traditional receiver that is all in MATLAB and another time to Pronto-based receiver. So we can see that in the blue columns, there is a difference between CFO that is estimated by Pronto and core CFO that is estimated by traditional receiver. So this is the error that we were talking about. But also, if you look at the red columns, you can see that fine CFO that for both receivers happen using traditional blocks is also different. So if you look at the final column, that is coarse plus fine CFO, that is the total CFO that ultimately gets compensated on the whole signal, you can see that these values are exactly the same. This means that the small error in core CFO estimation is compensated during fine CFO estimation. Therefore, no bit error rate degradation happens using Pronto. So Pronto is able to decode the waveforms that do not have the first field of preambles, have a shorter preamble, without imposing any bit error rate degradation. Here in this last slide, for this work, we have implemented Pronto on different CPU and GPU platforms, and we are reporting some timing results. The gist is GPU implementation with proper parallelization provides runtimes as small as 15 microseconds and 20 microseconds for packet detection and core CFO estimation, respectively, which enables Pronto to keep up with commercial Wi-Fi cards. So this is from the perspective of practicality. So now that part 1 and 2 are over, we go into part 3 to share my vision for the future work. These are just high-level visions. First, future direction that I would like to pursue is on the AI native air interface. That is the predicted paradigm for 6G communication. It is nothing but neural network-based receivers, but not only receivers, but also transmitters and everything. So the benefits that this kind of paradigm for 6G communication has is that we can have more flexible waveforms. We are not restricted to standard waveforms anymore. You can be creative, have any type of waveform, and just teach your train, actually, your receiver to decode that. And not only that, but also the data and application path, since both of them are neural network, now they can be fused together. So like both data decoding and some application like waveform classification or RF fingerprinting can be all fused into one neural network. And it provides a lot of flexibility, and there are a lot of research opportunities in this area. Currently, different companies such as NVIDIA, Interdigital, Ericsson, and DeepSig are working in this research and publishing papers. So one of the challenges that I have identified with the AI native air interface is the maintenance issue. We know that neural network-based receivers provide better bit error rates compared to the traditional receivers, but only if they are deployed in the same environment and conditions that they were trained on. If you change the environment, their performance might drastically drop. So now the question is, can we detect the performance drop due to the environment change? And if we detect this performance drop, can we recover from a malfunctioning receiver? The high-level solution that we have is shown here. The green part is already in the literature where you have a neural network-based receiver. We propose to put this framework on top of this, that is just a maintenance framework. In this framework, a monitor neural network is constantly running to detect the changes in the environment. And as soon as a change is detected, it activates a traditional receiver. Then the output of the neural network-based receiver and traditional receiver are compared. And if the neural network-based receiver is overperforming in terms of bit error rate, we just keep going with using a neural network-based receiver. If not, we have to design a way to retrain the neural network-based receiver. The key points about our proposed method is that performance comparison between neural network-based receiver and traditional receiver happens without having the true labels, the true bits, because we are at the deployment time and we don't have the true bits. Otherwise, we wouldn't need decoding in the first place. So that was direction one on AI native air interface. And another direction that is a really hot topic these days is open radio access networks. So radio access networks are an essential part of mobile networks that use cellular connection to connect mobile devices to the core of the network. So in traditional RANs, hardware and software are integrated together, and there is very little or no flexibility. However, the idea of Open RAN is having openness and intelligence. So machine learning is an inseparable part of Open RAN. And also the interfaces are opened between the software and hardware. So there is a lot of flexibility that different vendors can create different components or different hardware or software components for this architecture. Open RAN has its certain components and architecture. And there is near real-time rig and non-real-time rig, which is which has a longer latency requirement and is proper for orchestration and automation. These are connected together through certain interfaces. So with research in this area, there are some limitations that you need to be aware of. Certain interfaces just impose certain part of the data in the processing chain. But there are many opportunities. Like one of them is that because we have this longer constraint in the non-real-time rig, it could be used for retraining and adapting the neural network. So you can have near real-time rig for deploying your neural networks in the ORAN architecture, and then you can have them adapted to new waveforms, new signals, new traffic, whatever, using the capabilities within the non-real-time rig. So that was the last future direction. In this talk today, you saw my research, which was in the scope of application of deep learning in the physical layer. You saw part one, which was signal classification, 2 use cases from this part, waveform classification in the CBR span, and UAV RF fingerprinting. Part 2, which was wireless receiver design, and you saw our proposal for improving the communication throughput. You saw my future work vision, which was on the maintenance in AI native air interface and on ORAN systems. Here is the list of my publications during PhD, where I am lead author, and here is the list where I am co-author. Thank you for listening.
Hey, thanks for the presentation. I can see that we already have some questions on the chat. So the first question from Rajendra, the question is about, did you have done validation of your model by live capturing using USRP? I believe the question is about the waveform classification, or RF, I believe it's waveform classification.
Yeah, that's true.
Okay.
Let me try to get out of this and see. Okay. Is about waveform classification. If I can, if you could please repeat the question about waveform, I just go up.
Yeah, Rajendra, do you want to ask the question directly?
Sure.
Yeah.
Thank you for your presentation. It was a nice presentation. So I have a concern, like for the validation of your model, did you test it your model with the live capturing the RF signals and tested whether it's actually how efficiently it works or not?
Yes. So thank you for the question. Not in the Waldo paper, but I am a co-author in 2 other papers that have live capturing of data. And yes, it works, but the thing is we have to also train on live captured or real world data. But since we have spectrograms, we are lucky because they are less susceptible to changes in the channel. They are more robust to environment changes, and subtle changes in the environment will not impact the spectrogram so much, but you also have to train on real life data.
Thank you very much. And also, like you mentioned, like you have like for your training spectrogram, you measure with 100 megahertz bandwidth, I guess.
Yes.
So you tested with the same parameter, or you just changes, because like in a live environment there might be a different bandwidth frequencies, right? So
Completely. Yeah.
so you tested with the different bands or with the same, making with the same parameters?
Yeah, thank you. That was also a great question. We chose this 100 megahertz because we wanted to see the CBRS band in one shot. But you can also have lower bandwidths, as we have in other works, because there we were working on real data and we had limitations sampling like our radios did not have 100 megahertz sampling frequency, like you said. So if whatever you train on, you have to test on the same configurations. That's one of the limitations of the neural network. So if you look at the same spectrogram, but with a different, if you sample it with, if you look at the same scene, but with a different sampling frequency, you will still have this. It will just be a little stretched. So the shape of the signals will be a little different. So we were also, I also did some explorations with this that were not published yet, that you could actually train on a high bandwidth like this, but test on lower bandwidths. However, during training, you need to artificially modify your data and like crop this part perhaps and just stretch it just to mimic the low bandwidth. Those are some data augmentation methods that are sort of like novel and you can use, but in general, you have to be testing with the same configurations that you have trained on so that your spectrograms look the same and so that your neural network can detect them in deployment time.
Thank you. I would like to add one question on it. Like, you converted your RF signal into a spectrogram. So basically RF signal into the images, right? So while converting and testing with that images, do you think does it lose some form of information while converting from RF to the image part and training with a neural network?
Yes. Thank you again for the question. Yes, of course, the spectrograms do not have the phase information that lies within the IQ samples. That is why for very subtle detections, like what we were doing for RF fingerprinting, we were trying to classify devices based on very subtle distortions that are also within the phase information. I don't think, I mean, for them, having a spectrogram is not a good idea at all because you're already losing a lot of information. However, for waveform classification, where you really have distinct patterns, if you look at LTE and 5G, they really look different. Losing phase information is not an issue. In fact, in some cases, spectrogram-based detection provides some good advantages. One of them is the channel thing that I mentioned, because spectrograms are a little more robust to channel changes compared to raw IQ samples that get completely messed up. Another thing is preserving privacy. So there might be some certain situations where the receiver is not willing to impose the received IQ samples to you. You don't always have the SDRs where you can program and get the data wherever you want in the receiver chain. Sometimes you just have access to the spectrograms, which are good because they preserve the privacy of the users. So with them, I want to say that you still have the chance to classify waveforms with the spectrograms. But yes, that is correct that you lose information and it is not good for some applications.
Thank you for your answer. If you don't mind, like, have you done like how much a percentage of information you lose? Like, if you have done something on that, can you just mention over here?
When you record some signal, you have magnitude information and phase information. You lose all the phase information when you have spectrograms. So you just have the magnitude of IQ samples. And again, depending on your window size that you use for FFT, you are also compressing your magnitude of signal a little bit. But phase information is for sure all lost. I haven't done calculation on how much of the magnitude you are losing because of those window sizes that you do for FFT and creating your spectrogram. But I think that should be something standard that you can find out in different spectrogram creation methods. I mean, there are not many methods, but just the window size, it will give you some back of the envelope calculations for how much of the magnitude information you are losing.
So
I
in the
haven't done
interest
that
of
though.
time, let's quickly go through the remaining question. The next question is from Sid. For spectrum sharing involving 5G, we need to consider latency requirements for URLLC applications. Does your waveform classification scheme consider this requirement? And what would be the overhead in terms of latency be like?
Yeah, that's a great question. Thank you. I haven't, no, we haven't looked at that. We know that we have to have fast sampling and fast detection and fast spectrogram creation for doing these waveform detection, but we haven't numerically considered that in this simulated paper.
Okay, so I see there's a question from Hanif. Hanif, do you want to unmute yourself and ask?
Yeah, so wonderful presentation, very exciting work. I have tons of questions, but I picked one of those, and that's so LSTFs in Wi-Fi used primarily for packet detection and core CFO estimation, but they're also used for fast automatic gain control locking, as well as A to D conversion before it gets to the LTF part and then the SIG part and so on and so forth. I wonder, have you also studied the impact of eliminating LSTF on these functions?
Thank you for the question. No, not on the gain, but I assume that shouldn't be something as complex as core CFO estimation that we are doing. So you will still have access to the fixed sequence of LLTF when you remove LSTF. So I understand that there are benefits within the LSTF pattern because it's a short training symbol, but you can still do some of those functions through non-neural network methods, some of that gain control with LLTF, I assume.
Okay, thank you. Yeah, I mean, you're right. So the SDFs have that low peak to average power ratio. So they are uniform, they are easier for doing some of those functions. And it is, I guess, it would be interesting to explore how LTFs can also be used for these purposes, despite having higher peak to average power ratio and a little bit different, a little bit irregular pattern compared to SDFs. Yeah, thanks again.
Thank you.
So the next question is from Mojumdar Haidar. Nice presentation. The question is, did you try with other deep learning models to get better performance than YOLO model in part 1 classification?
Yeah. So I should go here. So we used YOLO version 3 here. No, I didn't try with other older versions of YOLO. However, no, I didn't try it empirically, but I was seeing that YOLO version 3 was the last version that was released by the main author. So I just stuck with that. The main creator of YOLO. Others are by other authors, but I know that there have been some improvements in detecting smaller objects, but still that is, I don't think, based on other data sets, image data sets, not RF data set, I don't think that is completely solved with other YOLO versions either. So I believe there would be still some limitations, even when using other versions of YOLO, but I haven't practically tried that, no.
Okay, so one last question for today. How AI ML can be used to compute inter-symbol gap? So Hassam, are you here?
That's a new.
Here.
Okay.
So between there is the guard time for the symbol or FDM symbol, and I have seen some research about how you can exchange dynamically this guard time or the enter between two symbols. And I was thinking, if we do it dynamically, how AI ML can do that.
Right. And thank you for the question. I haven't directly worked in that area, and I hadn't seen those literatures. But that seems like a very interesting area. So I can say that generally AI ML provides, like I said, a lot of opportunities to have newer waveforms, modify waveforms, or these kind of variations in different parameters, such as the inter-symbol guard that you said. So I believe that that is something that could be tried and worked on. I haven't worked on that area specifically yet.
But my last thing, in general, AI ML algorithm, how it can be used by the PHY. So I understand that maybe you can execute those algorithms maybe in software or hardware, like some accelerators. But
Yes.
how you dynamically, how you execute these algorithms in the actual PHY?
Well, you can imagine a specialized hardware for the receivers, for example, implemented on FPGA. When you receive the data on an FPGA board, there is, it gives you, inside the FPGA, it gives you the digital signal, and it is the raw signal. So you have to implement all of those receiver blocks inside the FPGA, or there are IPs for that maybe. So in there, you have access to all of these steps, and you can deploy your neural network also on the FPGA. And it can run in the same chip, on the same chip as you have receiver. So this is with FPGA, something that also students can go out and try. But for industry, maybe if they are done with the prototype and they have a design that works with like dynamic, I don't know, dynamic guards, maybe they can build a chip. So a custom chip needs to be built ultimately. But if you want to just try your prototype, you can use FPGAs, where the neural network and the receiver can run on the same chip. So they can still be deployed in the same hardware that has access to every step in the physical layer.
So anyway, because we're running out of time, do you have an email address? Because I did some work with Stanford on this machine learning stuff for the PHY, and I think we can benefit from your expertise. So if you put your email address, I can.
Yes, of course. Should I write it here? I don't know. My Northeastern email is, I can also put it in the chat.
Yeah, sure.
Or let me see, chat.
So I have put it in the chat.
Oh, thank you.
Hopefully I put the right address. Okay, it's not the right address. I think I messed it up.
Yeah, that's my website, but also
Okay.
northeastern.edu.
GitHub.io. Okay.
That's, yeah, the github.io is my website. There's my email and LinkedIn and everything in there. But also, if you want my email address separately, I just put it in the chat.
Thank you very much.
All right,
Of
so this is the
course.
first time we went over 10 minutes. So that's how good your presentation was.
I
And
hope it was good and not unclear.
yeah, actually, I also had a lot of questions, but unfortunately, we don't have time. But we have one last question from Fauzi. I'm not sure whether I'm pronouncing it correctly. Have you explored other AI/ML techniques which can be simpler and faster than neural networks?
Yes, thank you for the question. We have tried some simple ML techniques like SVMs for, not me personally, but the previous literature before me. They have done some explorations on using simple machine learning models, but they were never able to provide good accuracy for something as complex as RF fingerprinting. So for example, RF fingerprinting is very challenging, detecting those subtle distortions, and really a big neural network was required. So these are that I am showing you here, 77%. We are using two different neural networks. One is forward convolutional, another one is ResNet 50, and the 1D version of it. This is a huge neural network. I mean, with 16, 18, I mean, it's huge for me, for wireless applications that are usually 1D. So this is like 18 million parameters, and it is giving us this accuracy. But the smaller version that is just forward, it is giving us 52. So you can imagine as you go smaller or as you go less complex with the ML algorithm, it will not be able to provide comparable accuracy for you. So in some of these applications, yes, we have tried less complex ML algorithms. However, they haven't appeared as successful. So they were no competitors for neural networks.
All right. Thank you, Nasim.
Thank you.
Okay, so thanks again for joining us and sharing your research with us. I certainly learned a lot. I have a lot more questions to begin with, like when you started. Now I have a lot more questions, but maybe someday we can discuss about this research further in the future.
Of course, thank you for the kind words, and thank you everyone for being here and listening to my presentation. And feel free to reach out to me if you have any questions. I put my email in the chat, and my website, also Moinul put my website there. I am available for any questions. Thank you.
All right, take care. Bye, everyone.
Thank you. Bye.